So we will talk about PN junction diode. So suppose these are some silicon crystals. So these silicon crystals we can convert it into a PN junction by doping it with p-type and n-type impurities. And suppose we are doping this with p-type and this we are doping with n-type impurities, and we are joining them both. Okay, and a PN junction is formed. Okay, so as you all know, in the p side, the holes will be the majority carriers, and in the n side the electrons will be the majority carriers. So what happens is, like, when we join these p and n regions, the electrons from the n side, electrons are in the majority carriers here, the electrons from the n side will start moving to the p side. We call it diffusing. And since these electrons are minority carriers on the p side, they will be surrounded by a lot of holes. See, a lot of holes will be on the p side. So when an electron gets here, it is surrounded by a lot of holes. So what happens, the and the electron will combine and it will become an ion like this. So that is what happens. So when electron diffuses across the junction, it creates two ions. So when this electron goes from here to here, it creates a positive ion here, and when it reaches here, it will create a negative ion here. Okay, I hope you are clear with this till now. So when the electron enters the p-type p side, it will recombine with the whole of the trivalent atom. So you know that p-type is doped with a trivalent atom. So one hole, the vacancy is there for a hole. The electron enters and combines with the hole. So now the trivalent atom becomes a negative ion. So every time when the electron diffuses from the p side to the n side, sorry, from n side to the p side, it creates one positive and negative ion near the junction. See, with one electron from here is going to the p side, it will be creating a positive ion here and a negative ion over here, as we have already discussed. And near the junction also it will be creating, suppose a lot of electrons are going, so this is what happens. Near the junction it will create some positive ions, and near the this junction it will create some negative ions. These are immovable ions due to the recombination of the electrons in holes. So due to the recombination, um, this junction won't be having any charge carriers. Only very small amount, very few charge carriers will be there at this junction. So these ions will be setting up an electric field. So this is a positive charge, so from positive to negative there will be a electric field. So this will be the direction of the electric field from positive to negative. So only few electrons from n region and few holes from p region will be able to cross this junction due to the electric field. And so this acts as this region is depleted of carriers. That is why it is called the depletion region. And due to this electric field, there won't be any flow of electrons from n to p and from holes from p to n, and it creates a barrier for the flow of the charges, and that we call it as barrier potential or the built-in potential. So the majority carriers cannot cross this junction, okay, this junction, due to this barrier potential. So for example, for silicon it is 0.6 and germanium it is 0.3. So what happens is, like, that we have to apply an external voltage which is more than that barrier potential. Suppose for silicon it is zero point 0.6 volt, and we are applying an external voltage which is more than 0.6 volt. Then the electrons and holes will be able to move crossing this depletion region. But without any external bias, only very few majority carriers will be able to cross the depletion region, and minority carriers will be able to cross the depletion region due to this electric field. Suppose in n type here the minority carriers are holes. So these holes, will be getting attracted to the attracted to the p side, and similarly the electrons in p region, which are the minority carriers here, they will get attracted to this n region. So the minority charge carriers will flow due to this electric field. So we can see like the majority current flows through diffusion, and the minority current will be flowing because of this particular electric field. But both these will be cancelling out each other, and the net current in the circuit will be zero. So that is the first case. And the second case, we will be applying a external voltage. So we will be applying first in a direction opposite to the built-in electric field. We will be applying an external electric field. See, so here the in that case, no, that the diode will be in forward bias condition. See, we are applying positive terminal to the p side and negative to the n side. So what happens is, as the voltage is suppose it's a silicon crystal, and if that barrier potential is 0.6 or 0.7, whatever it may, 0.7 volt, suppose we imagine it is 0.7 volt, and this voltage is greater than 0.7 volt, then what happens? Then the depletion region will decrease. The resistance offered by the depletion region will decreases, and the electron can cross the depletion region very easily, and the holes can cross the depletion region from the p side, and electrons from the n side can cross the depletion region. So what happens is, the electrons, they will cross the, see, the electrons are the majority carriers here, so more voltage is applied here, so the depletion region width got reduced. See, this much was a width, now it is reduced to this much, and the electrons from the n side will cross this and will come to the p side. And from p side, what happens? The electrons on the p side, they will get attracted to the positive terminal of the battery. Similarly, the holes at the p side, they diffuse to the inside, and on reaching inside, what happens? They will be getting attracted to the negative terminal of the battery. So there will be a current flow due to the movement of both electrons and holes. So more voltage is applied, then more electrons and more holes will move like this, and there will be a greater current flow. Now the second case, we are applying an electric field. So we are applying a voltage, external voltage, in the direction of the built-in electric field. So that is the reverse bias condition actually. So the p type will be connected to the negative terminal, and n type to the positive terminal of the battery. So what happens is, like, we are increasing this voltage, and what happens is the width of the depletion region will increase, because it is it is in the same direction as the built-in electric field. So more voltage is applied, this depletion region will get increased, its width also increases, and the electrons gets attracted to the positive terminal of the battery, the holes on p side to the negative terminal of the battery, and this implies like more ions will get created across the junction. We will be getting more ions here. So in reverse bias, there won't be any flow of current due to the majority carriers, but due to the built-in electric field, the minority carriers crosses the junction, which we have already discussed. Like, due to the built-in electric field, there will always be a flow of minority carriers. So the holes will move to the n side, and they will get attracted to the positive terminal. The holes will move to the inside, and they will get attracted to the negative terminal of the battery, and similarly the electrons will move from the p's the holes are moving to the inside, and they will be getting attracted to the sorry, it's like, the holes are the minority carriers in the n region. They will cross the depletion region, and they will go to the p type, and they will get attracted to the negative terminal of the battery. Similarly, in the p region, electrons are the minority, they will cross the depletion region, and they will reach the n side, and they will get attracted to the positive terminal of the battery. So there will be a current flow due to the minority carriers, but this current flow is very, very, very less in the amount of microamperes. So the reverse bias current will be always very less in microamperes, and this current flow, this current is called the reverse saturation current, because the current will be reaching a saturation, like whenever we increase the voltage, the current will not be having much change. That is what it is called a saturation current. And as you increase the temperature, this reverse saturation current also increases. I told you, like, it is called the reverse saturation current. But what happens is that there is a maximum limit on the reverse voltage that can be applied to a p-n junction. So if he increases the voltage beyond a particular limit, called the which beyond a particular voltage called the breakdown voltage, the diode will break down. See, so the in forward bias, it was operating in this forward region, and the reverse bias, reverse saturation current, it was operating in the reverse region. So once the voltage reaches a threshold called the breakdown voltage, it will be operating in the breakdown region, and eventually the diode gets damaged. And this is generally called avalanche breakdown. And there are diodes which are specifically designed to operate in this particular region. Example is Zener diode is one of them. So what happens in Zener diode is, like, it's a heavily doped diode, and its breakdown region is not here. It will be less than that breakdown voltage. It will be less than this. It will be somewhere here. So that is it. Thank you.